All right, let's jump right into this. Sometimes the biggest mysteries are found in the tiniest places. And in this case, we're talking about a speck of gold. A speck so small you can't even imagine it. But inside, scientists found a puzzle that pretty much bends the rules of reality as we know it. And it forces us to ask this really profound question: how in the world do you tie a knot in infinity?
Okay, so to really get what's so weird about this, you've got to understand that in the quantum world, things usually fall into one of two camps, right? On one side, you've got your simple molecules. They have a set number of energy states. They're neat, they're predictable, they're finite. And then on the other side, you've got something like a big chunk of metal, say a gold bar. Its electrons exist in this just sea of continuous, practically infinite states. It's complex, it's messy, so things are usually one or the other, simple and finite, or complex and infinite. But then there's this thing, this Au-144 nanocluster. We're talking about a tiny particle made of just 144 gold atoms, and it's only 1.7 nanometers wide. I mean, that is just ridiculously small. So by all rights, it should act like a simple, predictable molecule. But it just doesn't.
And that right there, that's the central paradox that has had scientists scratching their heads. This little gold cluster is somehow showing signs of being both. It's got the clean, distinct energy levels you'd expect from a molecule, but at the same time, it seems to be tapping into that chaotic, infinite-like complexity of a big piece of metal. So the big question is, how is that even possible? Okay, so to get our heads around this pretty wild idea, we're going to lean on a really simple but powerful analogy. We're going to try to understand this quantum puzzle by thinking about, of all things, knots. So I want you to just imagine an infinitely long piece of string, okay? It has no beginning, no end, it just goes on forever in both directions. Now, this string, it represents a sea of infinite possibilities, right? Just endless potential. It's pure, unstructured, well, chaos. Now, what happens if we take that infinite potential and we apply a very specific set of rules to it? A set of constraints on how it's allowed to fold and twist. Well, all of a sudden, out of that endless, chaotic line, a stable, finite shape just emerges. A knot. So here's the really crucial point, the main takeaway from this analogy. The knot itself is a finite, structured object, right? But it's born from an infinite potential. It only exists because we applied a set of rules to that infinity. It's literally structure being pulled out of chaos. Just keep that idea in your head because it's going to be important. All right, so how does this whole idea of a knot in a string actually help us with our little gold puzzle? Well, this is where it gets really cool. Researchers developed a formal scientific framework they call the theory of infinity. And what it does is it takes this simple analogy and maps it directly onto the hardcore quantum physics of that gold cluster. Now, this theory is built on 4 core concepts. And yeah, they've got some pretty fancy sounding names, but don't worry, they're not that complicated. We've got pi, phi, k infinity, and g. And the great thing is, every single one of these connects right back to our simple analogy of tying a knot. So let's break them down, one by one. First up, we have psi, which is called the infinite plenum. This is easy, this is our infinite string. In the quantum world of the nanocluster, psi represents that vast, messy sea of all possible energy states that the electrons could theoretically be in. It's just the raw, untapped potential. Okay, next is phi, the symmetry operator. And if psi is the string, then phi is the act of tying the knot. See, for our gold cluster, those 144 gold atoms aren't just a random jumble. They're arranged in this incredibly precise, almost soccer ball-like shape. And this strict physical symmetry, well, that acts as the rules of the game, forcing all those infinite electron states into very specific, organized patterns. So, when you apply those rules, when phi acts on psi, you get k infinity, or knot infinity. And you guessed it, this is the stable knot itself. It's the special, super stable electronic state right at the core of the cluster, and it only exists because of those symmetry rules. It's like a tiny, protected island of stability that's been pulled out of that infinite sea of possibilities. And finally, there's G, the golden set. Now what's this? Well, think of it as the tension in the rope that keeps the knot from coming undone.
For the real gold cluster, this G is a protective outer shell made of 60 organic molecules. They basically wrap around the core and vibrate in just the right way to shield it, to stabilize that quantum knot and keep it from unraveling back into total chaos. So there you have it. It's a really beautiful theory, right? You start with an infinite potential, you constrain it with symmetry, and that creates a stable knot, which is then held in place by a protective shell. It all fits together so nicely. But the big question is, does it actually work? Does it explain the weird data? Let's go back to the original puzzle and check the evidence. And really, this is the moment of truth for any scientific theory, isn't it? Does this kind of abstract, beautiful idea about quantum knots actually match up with the bizarre signals that scientists were measuring in the lab? Let's find out. Okay, so when the scientists zapped the cluster with a magnetic field, this is the data they got. You can just think of this G factor as a way to measure how magnetic the electrons are. Now you can see most of these peaks are hovering right around a value of 2. That's totally normal, exactly what you'd expect. But then, just look at peak 8. It's not just a little different, it's a massive outlier. Yeah, that value is 4.4. That's more than double what it should be. For years, this ridiculously huge magnetic signal was a complete mystery. I mean, where on earth could something like that be coming from? Well, according to this new theory, that signal isn't an error at all. It's the smoking gun. In fact, a quote from the actual research paper calls this the definitive signature of, you guessed it, not infinity. That superstable core state, or K-infinity knot, it's so perfectly protected by the symmetry around it that its magnetic properties aren't quenched or dampened like they normally would be. And that's what produces this absolutely giant signal. But hold on, that wasn't the only weird thing going on. There was a second piece to this puzzle. Scientists also noticed this strange, almost clockwork-like rhythm in the energy readings from the cluster. And you know, a good theory can't just explain one piece of the evidence, it's gotta explain everything. What the data showed was this incredibly regular repeating pattern. The energy peaks were spaced out by almost exactly 100 millielectron volts, just over and over and over again. That kind of perfect rhythm, it strongly suggested something was acting like a metronome, keeping a steady beat. And yep, the theory of infinity has an answer for that, too. That rhythm, that's the beat of the golden set. It's the sound of those stabilizing vibrations from the protective outer shell of 60 molecules. It's the G from our theory, the part that holds the whole knot together. See? It's all connected. So, okay, this theory perfectly explains all the weirdness going on in one tiny, tiny speck of gold. But why should any of us care? Why does it matter? Well, because this isn't really just about gold. This is about a fundamentally new way of thinking about how the world works. What this gives us is a whole new toolkit for thinking. It lets us treat infinity not as some abstract math concept, but as a raw material, something we can actually shape and build with. It's an amazing framework for understanding how incredible complexity, I'm talking everything from life itself to maybe even consciousness, can emerge from just a few simple rules. And this isn't just some philosophical navel-gazing. It's a practical design principle. I mean, just imagine creating ultra-stable qubits for quantum computers, or designing brand new chemical catalysts from scratch, all by learning how to tie these fundamental knots in reality itself. And that leaves us with a final, pretty mind-bending thought. The universe all around us is just filled with this infinite, chaotic potential. But what we're starting to realize is that we might actually have a blueprint for how to tame it, a way to give it structure and form. So the question is, if we can truly master this art of tying matter and energy into these perfect, protected knots, what impossible, what truly beautiful things could we build next?